In the olden days, all you needed to do science was an apple tree to sit under and some kind of falling object. It worked for everyone, from Galileo to Newton. But as technology advanced and we began to look deeper, both out into the universe and down into the very makeup of life and matter, things began to get a little more complicated. And complicated cost cold hard cash. The US currently spends about $500 billion every year on research and development. About half of that is for defense, and a quarter is for health. The rest is split up in a variety of ways, covering things like NASA, energy, agriculture, and so on. Today we're looking at science projects that swallowed cash like a black hole. ISS. Racing around the world over 15 times a day is mankind's only home away from home. The International Space Station now has been occupied continuously for over 15 years, since the arrival of Expedition 1 on November 2, 2000. The first changes of construction began in 1998, and now over 400 tons of pods, panels, and instruments are orbiting over 250 miles above your head. So what are they doing up there other than staring into your back garden and playing chess? Well, apart from the obvious advancements of space technology, the station has also been used to look into everything from dark matter to tackling cancer, preserving the oceans, and improving certain vaccines. It's also inspired a lot of kids through a wide variety of education projects and laid the foundations of commercial space companies such as Elon Musk's SpaceX, which may one day take us to Mars. But it's really no surprise that hauling all those parts up into space wasn't exactly free. It's estimated that over $100 billion has been spent on the ISS so far, and it's scheduled to continue orbiting until 2020. All space stations have a gradually decaying orbit. The ISS, for example, is getting 2 kilometers closer to the Earth every year, so the space agencies aim to control the descent safely into the ocean. The Chinese space station Tiangong-1 is still in orbit after its final manned mission in 2013. But as of March this year, the telemetry has failed, so there's no longer any way to control its eventual fall. Maybe it's time to reinforce your roof. Curiosity. When the time comes for us to move from a little caravan in space to a full-blown planetary holiday, it looks like Mars will be the site for our first family outing. But since there is no TripAdvisor for the solar system, we had to make our own explorer, the Mars Curiosity rover. It was given an initial 2-year mission to investigate Mars' Gale crater, where it landed on August 6, 2012. But probably because there wasn't enough money on Mars for it to comfortably retire, it continues to work to this day. It has a range of odd jobs, but its goal is to give us a better overview of the geology and surface conditions of the planet, especially relating to the possibility of life having ever been present there, and what life it would be able to sustain if humans decide to come and take over. The rover is much larger than it often looks. The photos kind of make it appear like Wall-E, but it's actually the size of a car, being 2.9 meters long and 2.7 meters wide, and weighs in at just under a ton. A lot of the module that took it to Mars was discarded, mostly when the rover was lowered down and then used small explosives to blow itself free. Now, that's how you land on a planet in style. All in all, the Curiosity rover project cost around $2.5 billion. Now this sounds like a lot, but if you consider that Mars is 350 million miles away, that works out at about $7 for every mile traveled. When Uber Galactic is up and running, maybe they'll get a better deal. In contrast to Curiosity, previous Mars missions ended up being a complete waste of $325.6 million though. The Mars Climate Orbiter was supposed to be the first Martian satellite, but it disintegrated on entry to the Mars atmosphere. It was due to the biggest rookie error of all time. One operating program used pounds, but another subsystem read the telemetry in the metric form, newtons. This was not NASA's proudest moment. CERN. Let's come back to Earth now, and even a little under it. The Large Hadron Collider is the world's largest machine, sat in a gigantic circular tunnel in Switzerland, 27 kilometers in circumference. It's run by CERN, the European Organization for Nuclear Research, but it's a truly international project with over 10,000 scientists and engineers from more than 100 countries. The enormous donut shape is to allow them to accelerate particles to just a fraction below the speed of light and then smash them together in an aim to recreate the conditions just after the Big Bang, where there was an enormous amount of energy and particles interacting in ways that rarely occur in the universe now. The biggest priority was to prove the existence of the Higgs boson. All matter in the world is made up of particles, and they typically have 3 properties: mass, spin, which affects how they interact when they collide, and charge. The opposite charges attract and similar charges repel each other. Now, if a particle has spin or charge, you can see it interacting with other particles, but for a long time it was suspected that there was something with mass but no spin or charge. It would give other particles some of their mass, and it would be very hard to find because it almost never reacts with anything. It's like finding a shy mouse in a techno rave. But on March 14th, 2013, they finally proved its existence. The whole project took 30 years to build and cost around $9 billion. And if you want to check out some of the data yourself, in April this year, the scientists just dumped 300 terabytes of raw data onto the internet. Just don't start downloading if you're busy today or tomorrow. Maybe take the week off actually. Tokamak. Another example of smashing things together now. In the south of France, scientists and engineers are constructing a machine called the tokamak, which has already cost over $14 billion, and it's not even due for completion until 2019 at the earliest. So it's safe to expect the number to rise considerably. With many other projects, it can be hard to explain to people what the exact benefits are and why we're spending all that cash to find a tiny particle or stare at an empty planet. But tokamak has an immediate and obvious benefit to everyone. If it is successful, they are hoping to achieve nuclear fission and to use the energy it produces as a clean and sustainable energy source for everyone to use. At the moment, nuclear power is made possible by nuclear fusion. This is where you split an atom and capture the energy. But to do it, you need unstable radioactive elements that are incredibly dangerous, and the waste you produce remains lethal for thousands of years afterwards. We can contain the waste, but you never know what will happen over that much time. Plus, there's always the chance of another Chernobyl disaster or a potential spill like at Fukushima. Nuclear fusion is far better in every way. Instead of splitting, you're colliding particles together. The energy release is much higher than with fission, and you can use completely safe materials, such as deuterium. Deuterium is an isotope of hydrogen. Hydrogen is made up of one proton and one electron. Deuterium is the same, except it also has a neutron in its nucleus. It's found in the ocean and is about 0.01% of the hydrogen there, which is a small percentage, but that's still a huge volume. The only problem is you basically need to contain a nuclear explosion, so maybe it's worth a few extra dollars to make sure we don't blow France in half. Quantum computer. Our next machine seems comparatively cheap when you consider it's only $15 million, which would barely buy you a hot lunch on the ISS. But that money is all for just one computer, a quantum computer. The D-Wave 2 is currently sitting in Canada and is housed in a 10-meter square room, but the aim is to store much more information in a smaller space, like we have seen throughout the history of computing. The trouble with regular computing is that you need wires when you get down to it. It's binary. You have single bits that are either on or off. But by using the weird phenomena of quantum mechanics, where you have particles and waves, there is the potential to store a far higher amount of information, because you are no longer restricted to just a 1 or a 0. The only problem is, it's still hotly debated whether it's actually any faster than a regular computer, since a laptop has been able to achieve similar computational speeds. Plus, with a laptop, you can carry it around and watch Netflix. The D-Wave 2 doesn't even have Skype. Our next project actually came in slightly under its estimates, costing $2.7 billion, which was $300 million less than what was initially projected. The Human Genome Project launched in 1990 and was declared complete in 2003. So what exactly were they trying to do? Well, here's a quick guide to genetics. Every organism has a unique DNA, which is a molecule that combines in pairs to make strands, called chromosomes. Sections of those strands define the characteristics for that organism. These are called genes. For humans, we have about 3.3 billion base pairs of DNA, around 20,000 genes, and 46 chromosomes. Together, this makes up the human genome. By sequencing all of this data, we are now able to look at what areas of the genome, and we're generally talking about genes here, cause specific characteristics. This is especially useful for targeting disease. Some of you might be wondering, so whose DNA did we use for the Human Genome Project? We don't actually know, which may be a good thing. Imagine if you found out that most of modern medical science was based on the DNA of your creepy high school janitor. For the project, researchers acquired samples from many donors and then randomly selected a few anonymously, so it's not known who exactly the source was. Advanced LIGO. Next is probably the most modern discovery, gravitational waves. The idea has been around since Einstein, and we've been using a thing called a laser interferometer gravitational wave observatory, or LIGO for short, since the 1980s, trying to prove the existence of these waves, but it never really got anywhere until we put some real money into it. In September 2015, a $620 million overhaul was completed, which had taken 5 years. And as we all know, money talks, because the first ever recording of gravitational waves happened within a couple of days of them turning on the new detectors. They didn't publish the findings until February 2016 since, you probably have to check these things a few times. So what is a gravitational wave, and how do you observe it? Well, every object has a gravitational field, but unless you're a planet or bigger, it's going to be very, very small. And if the object isn't accelerating or decelerating, which most planets, moons, stars, etc. aren't, then the field doesn't change, so you won't observe any waves. But fortunately for us, we found a black hole orbiting around another black hole, and in gravitational terms, this is like the noisiest house party in space. We measure it by bouncing a laser between mirrors up and down a few kilometers. This creates an interference pattern. The gravitational waves very slightly distorted the path of the laser, so we saw a change in the pattern. If you're thinking, who cares? Well, all of our current observations of the universe have been using electromagnetic waves, mainly light, so this is like we just discovered a whole new sense to use, like you could smell a movie or taste music. Californium-252. If you thought gold was expensive, you're right, but it's not even in the top 10 most expensive materials in the world. Heroin and rhino horn are above it, as well as the crème de la mer miracle cream and tritium, which gives those self-illuminating exit signs their green glow. But where gold is around $40 a gram and heroin around $100, Californium-252 is a massive $27 million per gram, so try not to get addicted. Californium is a radioactive element that was created in 1950 in Berkeley, California, hence its name. Its atomic number is 98, and it appears at room temperature as a silvery white metal. It's useful because it is a strong neutron emitter. A microgram produces 139 million neutrons per minute. It's used to treat certain types of brain and cervical cancers, as well as being part of the stand-up process for a nuclear reactor. Since you can't find it lying about on the ground, Californium-252 has to be artificially created, either in nuclear reactors or by using particle accelerators. That's why it comes with such a hefty price tag. If you get some, make sure you remember where you put it. James Webb Space Telescope. Another major space project now, with a replacement for the famous Hubble telescope. The James Webb Space Telescope is still in development and has caused some friction in Washington, where the House of Representatives voted to abandon it in 2011, with $3 billion sunk into it and 75% already in production. The Senate ended up finding a compromise, and its budget was capped at $8 billion, with a scheduled launch in October 2018. It's also expected to cost an additional $800 million to operate for 5 years. It's much like the Hubble telescope, but in the true American way, it's just supersized. For these telescopes, the key is the mirror, and while Hubble is 2.4 meters wide, the James Webb is 6.5 meters wide. It's arranged into a large disc made up of 18 hexagonal panels. The telescope will be placed on the far side of the Earth, further from the Sun, at a place called the L2 point. Here, the combined gravity of the Sun and the Earth allow us to pull it along with us at the same speed Earth orbits the Sun, even though it will be 1.5 million kilometers further out. The telescope will deploy a large shield to protect its mirror and keep the temperature low. This placement in large mirror will let us see further than ever before and hopefully glimpse some of the oldest stars in the universe and the early galaxies. Glibera. And we finish in the world of medicine with the world's most expensive drug. Glibera is a gene therapy that is used to treat familial lipoprotein lipase deficiency, a highly rare condition that affects only 1 in a million people, causing a painful swelling of the pancreas. Since it's so rare, the market is tiny, with only 200 patients in the entire EU, for example. So, if you want to get fixed up, it's going to cost you a massive $1.21 million per year. For that money, I'd expect an entirely new robotic body, not just a handful of pills. Right now, Glibera has not been approved in the US, so our most expensive medicine is Soliris, a treatment for a blood disorder that affects about 8,000 US citizens per year. It's a bargain compared to Glibera though, at just $440,000 annually. For more top lists like this, be sure to leave a like and subscribe if you haven't already, and don't forget to check out our other lists, and we'll see you all next time.